Hello, I am Chandrasen from the group 9. We present the question A and E. So this is our team member, Yo, Zong, and Hafizin.
Hello, my name is Hafizin Jamil. I will proceed to introduction of transfer function. As you can see on the slide, a transfer function is a representation of the relationship between the input and output of the system in frequency domain. It is commonly in used in electrical circuit and control system to analyze how a system responds to different frequency. The transfer function denoted as H omega is simply the ratio of the output to the input, or H omega equal Y omega divided by X omega. Why is this complex function so important? Because it completely characterizes the system. The magnitude tells us exactly how much our input signal amplitude will change, whether it is get amplified or flickered up. Meanwhile, the phase angle tells us how much the signal will slide or shift in time. On this slide, we are given a raw transfer function, and our goal is to convert it into the standard form required to draw a box plot. To convert a transfer function into a box plot, we use the straight line or asymptotic approximation method. To plot a box diagram easily using the straight line approximation, every term in the denominator need to be in the standard time constant form, which look like 1 plus j omega divide omega c. Where omega represents our corner frequency, let's walk through how we transform this function step by step. If you look at our denominator, we have two primary factors, a simple pole at j omega plus 5 and a second order pole at j omega plus 20 square. Standardize this, we factor out the constant. First, we pull out 5 out the first term, giving us 5 times 1 plus j omega divided 5. Next, we pull out 20 of the square term. Because of the exponent, it's come out with 20 square or 400, leaving us with 1 plus j omega 20 square inside. Now we simplify all the constant in denominator. 5 times 400 give us total constant of 2000. To find our final board gain, we call K. We take the original 300 and numerator and divide it by the 2000. We just factor it out. 300 divided by 2000 equal 0.15. This leads us to the final standard equation box at the bottom. H omega equal 0.5 j omega divide 1 plus j omega divide 5 times 1 plus j omega divided by 20 square.
Now I want to explain the magnitude plot. S omega is equal to 0.15, J omega 1 plus J omega divided by 5, 1 plus J omega 20 divided by 20 square. Magnitude dB is equal to 20 log S omega. The constant gain is the K equals to 0.15, and we place the calculator, the 0.15 is equal to negative 16.5 dB. The 0 at the origin J omega with a slope of positive 20 dB per decade. The pole omega equals to 5, the slope is negative 20 dB per decade is equal to 1 divided 1 plus j omega divided by 5. The double pole omega is equal to 20 with the slope is negative 40 dB per decade. equals to 1 over 1 plus j omega divided by 20 squared. Now I want to explain the magnetic plot. First, we need to see the green horizontal line here. For our constant gain k in calculator, we direct insert 20 log k 30 log 0.15 equal to negative 16.5 dB. So we direct draw a flat line and a negative 16.5 dB across the entire graph. Next is the zero at the origin, represented by flat slanted line. This gives us a constant outward slope of negative 20 dB per decade, crossing the 0 dB exactly at the omega equals to 1. Next, we encounter our simple pole at the omega equals to 5. So, by the line, blue line, it stays completely flat at the 0 dB until the omega reaches to 5. After that, it drops at the rate of negative 20 dB per decade. Moving forward to omega equal to 20, we have the double pole, indicated by the two purple line. Because this curve is square, so the effect also the square here. It stays flat until the omega is 20 and it drops to negative 40 dB per decade. Finally, we can get the magnetic response. The black line here, the black line got a positive 20 dB per decade and following going to 0. When omega reaches to 5, the first pole pull is out down by the negative 20 dB per decade. It perfectly cancels the outward slope, so the total response becomes completely flat between omega 5 and 20. Once omega hits 20, the double pole takes over. It drops out the flat line into a negative 40 dB per decade drop. So this shows our diagram here. Now I want to explain the phase plot. For the phase plot, we can simplify the sum of the individual angles to find the total response. First, the purple line stays at the 90 degree. Its constant phase leads from the zero at the origin. The green line is our constant gain. P is K is at a 0 degree phase shift. Next, we can see the red line is the single pole at the omega equals to 5. It creates a phase lag from 0 to negative 90 degree, crossing exactly through negative 45 degree at its corner omega. The blue line is the double pole at the omega equals to 20. Because it's square, so it creates a total phase lag of the 180 negative degree, passing exactly through the negative 90 degree at the omega equals to 20. Finally, we can see the black line is represent the total phase response. It starts at 90 degrees due to the zero as the omega increase. The combined lag from the both poles drop the curve downward. Ultimately, the settling at negative 180 degree at high omega is complete our analysis here. So conclude our analysis for question A. Here is a summary of our result. Looking at the magnetic dot plot, we can clearly see the initial positive 20 dB per decade divided by the simple zero. This leading a stable peak region at exactly negative 2.5 dB. It stays at a flat between 5 and 20. After the omega 20, the double pole takes over. pulling the magnetic down and drastically at negative 40 degrees per decade. For the phase dot plot, we track the asymptotic phase at the key of omega checkpoint, starting from 76.5 at the omega 1 radians per second, 63 at omega 2 radians per second, negative 31.5 degree at omega 10 radians per second, negative 72 degree at omega 20 radians per second. Next, 126 degree at omega 50 and last 180 degree at omega 200.
Hello guys, I believe that you guys know how to plot the graph using given transfer functions equation. But now let's reverse it. Can you imagine that the question show you magnitude plot instead of equation of transfer function? And yeah, here's come equation E. This question we need to extract an equation straight from a given plot. At first, looking at the horizontal axis, the coordinates represent the log of omega. By decoding these indices as power of 10, we unlock our system active frequency coordinates, that is, establishing sharp vertices at 1, 10, 100, and 1000 radians per second. Next, we use inverse asymptotic synthesis to decode our system roots from the slope modifications. How we figure out all zeros and poles? We can just simply look at the changes of the line. Below frequency of 10, our line falls at minus 20 decibels per decade, revealing a long pole at origin. At frequency of 10, the path shifts to a flat 0 decibels per decade, which is a net change of plus 20, indicating a simple zero. Another plus 20 change at frequency 100 confirms a second simple zero. Finally, at frequency 1000, the slope drops from plus 20 to minus 40. This net drop of minus 60 decibels per decade proves a third-order triple pole resides at this location. Okay, on this page, we calculate our system gain K. Tracing a plot, our low frequency line cross frequency 10 at exactly 20 decibels. Setting this up in its logarithmic form allows us to mathematically isolate K at exactly 100. By assembling our roots and clearing out all internal fractions from within our system brackets, we synthesize our final transfer function, leaving a clear scaling factor of 10 to the power of 8 in our numerator.
Hello, my name is Yosen Wei. I'm taking from my friends and we will talk about the discussions. First, transfer function is used to analyze the frequency response of a circuit where there is two Bob plot. The first is magnitude Bob plot, which shows the change in gains against frequency. The second is phase Bob plot, where it shows the change between phase angle and frequency. After that, we also notice there is a corner frequencies that determine the slope change point of a Bob plot. Lastly, we notice there are two other things. First is pole. The second one is zero, where pole cause a decrease in gain, while zero cause an increase in gain. And that's I conclude my discussion. Hi everyone, still remember me? Okay, we will continue with the conclusion. So, as a conclusion, we have mastered asymptotic straight line modeling technique for more efficiency, frequency, domain analysis, and bulk plot approximations. We also learn how to apply superposition construction rules to accurately determine the complex magnitude response points and critical phase transition point. After that, we also learn how to analyze the impact of repeated system roots on frequency response characteristics. That includes dynamic slope change caused by double pole, triple pole configurations. Lastly, we have familiar on how to use connected theoretical circuit analysis and transfer function algebra to practice frequency response visualizations and interpretations. That that's all from us. Thank you.